In our last video, we figured out how Mobius transformations could be used to represent the twist and rotation elements in the rational tangle group. What we want to do in this video is take that a step further with a particular choice of Mobius transformations for the twist and the rotation. We want to show that in fact we can represent a rational tangle not just by a composition of a bunch of functions, which can be really complicated and unwieldy to work with, but in fact we can use a single rational number to stand in the place of that function representation. That rational number will be called the fraction of a rational tangle. Let's see how it works and why it works. In the last activity, you discovered a bunch of different candidates that we could use to represent the twist T and the rotation R, Mobius transformations that interact with one another in the same way that the elements of the rational tangle group do. The canonical choice that we tend to make for this, and it's not the only choice we could make, but it's the one that's, in a sense, the simplest to work with, has the twist element represented by the function t of x equals x plus 1. So it's the add 1 function. That's a function that has infinite order. If we compose it with itself a bunch of times, we're adding 1 a bunch of times to its input, right? And that process never wraps us back around to the identity function e of x equals x. So that element has infinite order. And the canonical choice for rotation is the opposite reciprocal function, r of x equals minus 1 over x. That is a function that has order 2. If I compose it with itself, take the opposite reciprocal of the opposite reciprocal, I always get back to the original argument that I had. Right? So r composed with r is going to give me the identity function. These are going to be the Mobius transformations that stand in for our twist and our rotation. And so in this video, what I want to do is take an example of a rational tangle and look at how we might use this twist and this rotation to represent this rational tangle. And then make the case for why we don't need the whole function to represent it. We can get away with just a single rational number. So here's a sketch of the rational tangle t to the fourth r, t to the third r, t r, t squared. Right? So I did 4 twists and then a rotation, 3 twists and then another rotation, 1 twist and then a rotation, and then 2 twists and I'm done. So here's a sketch of that rational tangle. I want to find first a function that can represent that rational tangle that is built out of composition of these 2 functions in the same way that my rational tangle word is made out of those same generators. So to do that, we'll first build this function out of the alphabet of the functions little t and little r. Reading my tangle from left to right, as we usually do, the first thing I'm doing here is starting with an empty tangle, which we're going to represent with the identity function. And then we need to apply the twist 4 times in succession. If I apply the twist once, in other words, if I take and apply t of x to both sides of this equation, I get t composed with e of x. But remember, e of x is the identity function. So t composed with e is the same thing as just t, right? The identity function is invisible in composition. That's how identities work. So I just have t of x equals x plus 1. But I don't just have it once. I have it 4 times in a row. So I need to compose by t again, t of x. So I need to add 1 again. In other words, t composed with itself twice is going to give me the function t squared of x equals x plus 2. When I do it 4 times in a row, I'm going to be adding 1 4 times in a row. And so when I compose t of x with itself 4 times, I get the function that turns x into x plus 4. So far, my function composition representing t to the 4th power is the function t to the 4th of x equals x plus 4. The next step in my rational tangle word is a rotation. So I need to apply my r of x function, the opposite reciprocal. If I apply r to both sides of this equation, I get on the left side r composed with t to the 4th of x. On the right-hand side, I get the opposite reciprocal of x plus 4. And now I just keep going across the word. The next thing I'll do is apply t 3 times. In other words, I'm going to add the integer 3 to my expression. Then I'll apply r, which is an opposite reciprocal to the whole thing. Then I'll apply t once, so I'll add 1 to both sides. Then I'll take the opposite reciprocal again. Then I'll add 2 to apply t twice. And so at the end of that whole process, I have built this rather complex looking function that has represented the iterative process of first doing 4 twists and then a rotation, and then 3 more twists and then a rotation, and then 1 twist and then a rotation, and then 2 twists at the end. So this function is supposed to represent this rational tangle, which was built out of those same maneuvers. This kind of function is an example of a really exciting and well-studied class of functions in algebra and number theory called the continued fractions, right? It's built out of these iterative additions and subtractions followed by reciprocals. There's some great theory. Continued fractions are fascinating and very accessible subject in more generality. But this is a really complicated animal that we're trying to use here to represent a rational tangle. Functions are messy. And so what we'd like to do, if we can get away with doing it, is use not a whole function to represent a rational tangle, but a single rational number. And in fact, the fact that we can do this is what gives rational tangles their name. They're called rational tangles because, in fact, we can represent them with a single rational number. But a priori, it looks like we need an entire function from the rationals to the rationals to do it. So I have to prove why it is that we can get away with using only a single rational number instead of an entire function from the rationals to the rationals. Why is it that we can trade these nasty, messy functions for a single one of their values? In other words, a single rational number. How can a number, a single number, tell the same story about rational tangles that these nasty continued fraction rational functions do? So here's why. The reason why is embedded in this theorem. The theorem says that if I have a group H, and if that group is a group of invertible functions on the reals, you can substitute rationals there if you like, and if every non-identity function in that group is fixed point free, which I'll explain what that means in a moment, if every non-identity function is fixed point free, then every function in that group is uniquely determined by the value that function takes at f of 0. In other words, every different function that's a part of this group is going to have a different y-intercept when we graph it, and vice versa. So if you tell me the y-intercept in this group of functions, I can tell you what that entire function is. And so that means we don't have to care about all the functions, we just have to look at their y-intercepts, which are just going to be, for us, rational numbers. That there would be a one-to-one correspondence between rational numbers, which are the y-intercepts, and the rational functions, which generate those y-intercepts, is something that we can't expect to happen in general. Which is why we need this fixed point freedom criterion. And to unpack that, what fixed point free means is that the only function in my group here which intersects the line y equals x, the only function which when I put a given input in is going to give me that same input out, the only function which is going to satisfy f of x naught equals x naught for any value of x naught that I choose is going to be the identity function. If my function has a fixed point at all, if there's any real number which when I put it into one of my functions gives me the same number as output, then that function must have been the identity function. So the only function that even crosses the diagonal line y equals x in its graph is the identity function. That's a pretty strong condition. But it's a condition that we can prove, I'm not going to do it here, we can prove that the group which is generated out of this twist and this rotation function via the operation of composition is indeed fixed point free. So if we can show that every fixed point free group of invertible functions is uniquely determined by the values that they take at their y-intercepts, then this will be such an example, and we'll be able to have shown that my rational tangle functions, which I can represent by the continued fractions, can actually be uniquely determined by the values that they take when x is equal to 0. And that's going to be the greatest news of all. Let's prove why this theorem should be true. This is a handy argument in using function algebra. So what I want to show is that if I pick two functions g and h that are a part of my group, and if g and h have the same y-intercept, so if g of 0 is the same as h of 0, then I want to prove that that means that in fact g and h are the same function everywhere. Right? If they have the same y-intercept, then they're going to be the same function everywhere. For all x, g of x equals h of x. That's the burden of proof that I have here. Let's see how the proof works. If I take g of 0 and h of 0, that common y-intercept that my two functions have, and I give it a name, I'm going to call it a. So both g of 0 and h of 0 are equal to a. I'm going to define a new function f by the composition g inverse. Remember, all my functions are invertible, so g inverse is also a function. I'm going to take g inverse composed with h and call that function f. And I'm going to ask the question, what is f of 0? What's the x-intercept, the y-intercept of the function f of x? We'll use a definition of f. Right? F is g inverse composed with h. So f of 0 is g inverse of h of 0. But we know a name for h of 0. H of 0 is what we're calling a. So f of 0, g inverse of h of 0, is the same as g inverse of a. But what's g inverse of a? Remember how inverse functions work. Inverse functions reverse the roles of input and output. So g inverse of a is the output that the g function would give us if its input was a. Other way around. G inverse of a is an input which produces an output of a from the g function. Well, we happen to know that g of 0 is equal to a, and since g was an invertible function, that means g inverse of a would be equal to 0. So if I read this whole thing from left to right, we've just proven that f of 0 is equal to 0. And that's big news, because what that means is that f is a function which has a fixed point. It crosses the diagonal line y equals x. Namely, it crosses it at the point 0, 0. F of 0 is equal to 0. So f has a fixed point. But we have assumed that my group is a group of fixed point free functions. So the only function which is permitted to cross the diagonal line y equals x is the identity function. Therefore, by our fixed point free assumption, f, the entire function f of x, is the identity function e of x. F is equal to e. So f of x is equal to e of x for all values of x. But f was g inverse composed with h. Therefore, g inverse composed with h gives me the identity function. Now I'll apply the g function to both sides of this equation. G of g inverse of h of x equals g of e of x. And then just remember that g composed with g inverse, by definition of inverse, is going to give me the identity function e. So e composed with h of x is equal to g composed with e of x. But e is the identity function, which means whenever I compose e with anything, I get that same thing back. So e of h of x is nothing more than h of x, and g of e of x is nothing more than g of x. And we have proven that g of x is equal to h of x for all values of x. In other words, in any group of fixed point free invertible functions, the y-intercepts of those functions uniquely determine the entire functions themselves. Two functions cannot share a y-intercept unless they are the same function everywhere. What that tells us is that if we're convinced that the group which is built out of this t function and this r function as generators is indeed fixed point free, then that means that all functions in that group are determined uniquely by their y-intercept, in other words, the value of f of 0. So instead of worrying about the whole continued function nastiness, we can worry instead about just the values of those functions at x equals 0. Instead of building the function out of t's and r's, we're going to build the rational number that's obtained by evaluating that function at x equals 0. And we're going to call that the fraction of that rational tangle. So what is the fraction of this rational tangle? It is the value of this continued fraction function that we built evaluated at x equals 0. We're going to call that capital F of q. The fraction of the rational tangle q is going to be what I get by plugging a 0 in for x. And so when I evaluate this arithmetic all out, I add 4 to get 4, take the opposite reciprocal to get negative 1/4, add it to 3 to get 11/4, take the minus reciprocal to get negative 4 over 11, add 1 to get 7 over 11, take the opposite reciprocal to get negative 11 over 7, add 2 to it to get 3 over 7. And the rational number 3 over 7 is then a perfect representation of this rational tangle. Because what we've proven here is because of the uniqueness, every different rational tangle is going to have a different fraction associated with it, and vice versa. And so for however many rational tangles there are that exist in the world, there are exactly as many rational numbers, and every different pair of tangles gives me a different pair of rational numbers. Which means if I hand you a tangle, you can use this algorithm to produce the fraction of that tangle, which is a rational number. And conversely, if you hand me a rational number, a fraction, I can use this process backwards to produce for you the rational tangle that has that as its fraction. There is a one-to-one correspondence. So we have discovered here a complete invariant for rational tangles. Rational tangles are messy. Rational numbers are nice. And so now we have a dictionary for going back and forth between those two worlds. The questions we can ask about rational tangles, we can ask instead about rational numbers, and rational numbers are a lot easier to work with. So what you're going to get some practice doing here is just doing that translation back and forth, going from a rational tangle to its fraction, and then going from a rational number to the tangle of which it is the fraction.